下期找张建松来看。对，张建松买来不很好说的，对不对？All right， 我们今天还是有联网的，没有哈？有。OK，All right， 我们今天我们不联网以后就用中文讲了是吧？还是用英文讲？我都忘了，还是用还是英文啊？不联网，没有日本人是中文英文无所谓的哈。OK， 好，今天我要稍微早一点下课，我也有一点事。我们讲完这个以后就下课 ，OK， 讲到什么时候就算。大概我想10点钟会完。我们上一次last time we discussed deep water wave. Now we're going to talk about the governing equation. The difference between physical science and the biological science is that we have governing equation. You write up an equation, the equation covers all the changes. In biological science, we don't have the governing equation, so it's mostly based on observation. Chemistry is changing. Chemistry does not have the fundamental equation. The fundamental equation like physics, most of the physical phenomena, we either have Newtonian mechanics, F equal to ma, or electric magnetic Maxwell equation. Yeah, those are the fundamental equation. So the fundamental equation, to write down the fundamental equation, you have to make some assumptions. Yeah. Now, whether these assumptions are reasonable or not. Now, this is a very deep philosophic problem, as summarized by Albert Einstein again. Albert Einstein said this: everything should be made simple, but not simpler. What does it mean? It should be made simple, but not simpler. 你们这句话你们看了觉得怎么样？有没有为什么要叫 simple 跟 simpler？ 它的真正的意义就在，就是说我们要把一个事情都 make simple. That means we have to synthesize all the observation into a very simple, concise law. For example, everything's moving. We roll a ball. The water flow, we fire a gun, we fly airplane. All of these phenomena are very complicated, but we can make it simple. How? F equal to ma. Yeah, that governs everything. Yeah, so that's make everything simple. To look for the governing law. But in the process, you should not make simplified assumption. You should not simplify the thing. Leave this out, leave that out. Okay, that's what it says. So this sentence is very simple, but it's very deep, a very deep appreciation of physics. We should find the governing rule, but we should not make simplify or simpler assumptions. Yeah. Now, if we look at the governing equation, this is the KdV equation. In writing this, there are already certain assumptions already made, but still, this is a pretty general rule. But when we convert this to the so-called nonlinear Schrödinger equation, and we made another simplified assumption. What is the simplified assumption? We made the wave number and frequency are constant. Not only wave number and frequency are constant, its derivative is constant. Its second derivative is also constant. It's so constant that it's a no slope, no curvature. Okay? So this assumption, under this assumption, we can derive this equation. This equation is what we call the cubic nonlinear Schrödinger equation. So when people derive this and they get this, they are so happy. They say, aha, we get nonlinear Schrödinger equation. We can connect water wave with some fundamental physical law. Even though in physics, this nonlinear term is not there. It's just Schrödinger equations without the nonlinear term. Now we have a nonlinear Schrödinger equation. But this assumption, the wave number and frequency are constant. Prior to this, we thought this was very, very reasonable because water wave has a permanent shape. If it's a permanent shape, then the frequency is probably constant, even though it has some harmonics. But harmonics goes with fundamentals. But now we know what is frequency. In this approach, frequency is, by definition, is time derivative of phase function. And time derivative of phase function is not constant. Okay, so this assumption has problem. And if you make the wave number frequency to the second order, the second derivative is not constant, then you're going to have lots of extra terms. Yeah, you're going to have a time derivative of k. So your governing equation changed. And if further, if you made the wave number frequency of the first order, you have additional terms that comes up. So all of this make you think that is the nonlinear Schrödinger equation the final solution or the final governing equation? Probably not. Okay? So this is only for shallow water wave. For deep water wave, it's different. Deep water wave, the control equation is different. But this deep water wave is derived by Christian Dusty. He's a mathematician now at Bergen University in Norway. He made his famous discovery in 1979. He published a paper in Royal Society of London. It's not a very long paper, but in it, he derived the nonlinear Schrödinger equation to the fourth order. And you don't have to know, you don't have to remember how this thing is derived, but I just want to show you how involved it is. This is continuity equation. All water movement, if you neglect friction, it's incompressible and perfect fluid, and it's all can be simulated by a potential function, and the potential function satisfies Laplace equation. What makes water wave so complicated? The potential equation applied to all kinds of phenomena. Applied to water movement is applied to electromagnetic phenomena. What makes water wave complicate are the boundary conditions. the boundary condition at the surface, this is the dynamic boundary condition. That means the pressure has to be constant. Okay, and this is a continuity equation of velocity. Means, sorry, these are our dots. Somehow his computer does not pick up the math type equation. You don't have math type in your. That's why. Yeah, the math type gives you this dot product. These are dot products. So this is a vertical velocity equal to time derivative of surface plus horizontal gradient times the vertical gradient, yeah, of the surface. So these are the governing equation. Then you make assumptions that phi can be written as phi 0 plus phi 1, epsilon phi 1, epsilon phi 2. It's perturbation analysis. Then you first reduce the equation. Instead of z equal to zeta, zeta is unknown. You reduce the zeta into at the z equal to 0 with the Taylor series expansion. Okay, and then assuming phi equals to this basic form. When you make this basic form, this theta is 2 theta and plus so on and so forth. This again is a Fourier analysis, Fourier expansion. And this is the fundamental, this is the mean, this is the fundamental, and this is the harmonics. The second 2 theta. What 2 theta means? Theta equal k dot x minus omega t. What's 2 theta means? 2k dot x minus 2 omega t. Yeah. What is the propagation velocity? Propagation velocity is exactly like the fundamental waves. Yeah. Is it dispersive? No. Yeah. So all of this is exactly the harmonic terms. You can keep on going, but everything is written in the Fourier analysis. Why do you use Fourier analysis? Because Fourier analysis can have closed form, and it can actually put in the differential equation to be operated on. HHT cannot do this. Now, is this wrong? This is not totally wrong. But what the difference here, I have to stress, if you collect all the terms, and if you add all the terms together, the sum makes sense, but not each individual terms. Okay? But here, this assumption is theta is constant. And with that, we can derive the fourth order amplitude, the envelope amplitude equation. When you derive that, you see all the differentiation are with A, none are with theta. But if you think that you have, this is essentially saying that your carrier wave, this whole wave equation is talk about the governing quantity of A. It did not talk about frequency. Yeah. So what does it mean? That means that you tactically accept the assumption of wave of permanent shape. The water wave of permanent shape propagate does not change. Yeah. And we, at the very beginning, we show that there's no such a wave called water wave of permanent shape. So the water wave will change. Therefore, the permanent shape assumption has problem. But so, based on that assumption, you look at this equation. This equation, this assumption, this equation is all about A, nothing else. Yeah. So this is the kind of situation we got. All the published governing equations are in terms of envelope, and the carrier are assumed to be of constant frequency and of permanent shape. Yeah. The constant carrier frequency assumption is unattainable. It's not possible. We know it's not there. So if the carrier wave is not there, then you say you study the envelope. The envelope does not make any sense. So in addition to that, we are going to talk about wave direction. Up until now, the water wave that we treat is unidirectional. It's just one direction that's propagating. But if you look at in the ocean, you see the waves are not exactly one direction. Even though if you have experience stand on the shore or in a boat or ship, you see the wave propagating. You see the wave mostly propagating in one general direction. Does that mean wave is only one direction? No. If wave is one direction, the wave has to be an infinite long crest. The crest will never change. It's propagating in one direction. If the wave is short crested, the wave has, for example, three-dimensional shape. How can wave with three-dimensional waveform, if we have one wave propagate this way, the other wave propagate this way, and the cross pattern gives you three-dimensional wave. So short crested wave, the wave that has three-dimensional structure, means you have at least two directions, and maybe even more. Okay, so the waves are not unidirectional, and there are more problems concerning the directional wave developments. Yeah, and this wave development is critical because you see, now we talk about global warming. In global warming, there are two very important issues. The issue number one is temperature. So what temperature is increasing, okay? And why temperature is increasing? Because we have too much greenhouse gas. CO2, the majority part of CO2 is actually absorbed by the ocean. Yeah, so the ocean becomes a critical element in the global warming discussion, even from the greenhouse gas point of view. In fact, the ocean current, like a Kuroshio or Gulf Stream, actually move tremendous amount of heat from the equatorial region to the polar region. For example, you go to the east side of Atlantic. You look at the city like Norway. Norway, it's okay. It's actually in the winter time, Norway is not that cold. Sometimes it even rain and not snow. Yeah, the latitude of Norway is very, very high. Let's not forget about Norway. Let's pick London, for example. London's latitude, if you move London's latitude to American continent, it's 52 degrees. Yeah, and where it will locate? It is located in Hudson Bay. Hudson Bay is in Canada. There's absolutely ice, and if you dig within a couple of feet, you hit permanent frost. That means the ground is permanent ice. Even in the summertime, the ice disappeared, but not underground. A couple of feet, it's all ice. Why European is so mild and American is so cold? The European is mild because of the Gulf Stream. The Gulf Stream flow all the way up, carry all the warm water to Europe. So London is very inhabitable, and even Norway, Sweden, they are inhabitable. But northern Canada, you cannot live there. Yeah, so that's all due to ocean current. How the ocean current was generated? Ocean current is generated by wind. How the wind can put its stress or its momentum to the surface water to make it flow? It's caused by friction. the friction between air and water is very small. But how can they put so much energy in the ocean to generate such a large current? It's because the water surface is not flat. If water surface is flat, it's not going to cause so much energy and so much momentum to exchange. The water, once the wind starts to blow, water has wave. Once you have wave, more energy and more momentum is going to be transferred from air to water, because water wave, the wave itself, is a rough element. So the wind will be wind energy and wind force, momentum will be transferred across the air's interaction. And that is a course by itself in the earth science. Okay, so that influences surface stress, and that's very, very important. And if we look at it, see, when the wind blows on the ocean surface, how it generates wave, that is a very interesting problem. And that problem actually is not totally solved yet. Right now, our understanding is based on two theories. One is by Phillips. Phillips is my advisor. He made his name before he was, let's see, 30. Before he was 30 years old. He published two papers. One paper is the resonance interaction we discussed before. The second one is wind wave generation. Yeah. The resonance interaction was published when he was 30 years old. Not quite 30 years, but it was written, of course, before that. So before he was 30 years old, his best work, his most famous work was published. This is the second one. He said that when wind blows over the surface, only those waves can grow. Those waves will grow is omega equal to k dot u. Yeah. See, k is the wave number. U is the wind velocity. The only thing we know is wind velocity, right? So what kind of wave number and the frequency that will grow depends upon this. But then you also know the wave number and frequency has a dispersive relationship. Okay, so the only one frequency that you can generate, if you have very high frequency, that means the wave number is high, dot into u, k dot u equal to ku, k absolute value, u absolute value times cosine theta. So this cosine theta is the angle. If the wind blows in this direction, and if you want to generate it, this has another way to write it. If we divide each side by k, then we will see that this becomes phase velocity. Phase velocity becomes unit vector dot u. That means the phase velocity has to match the wind velocity in the wave direction. If it's in the wave direction, we know the short wave propagates very slow. The wind is always like 10 meters per second. So if you want to catch up this wind, you cannot generate a wave in the wind direction. You have to generate a wave in this direction. Then when you dot product, the component of the wave of the wind velocity is small. And if that component match up with the wave phase velocity, then that wave will grow. That is his second resonance theory, yeah, or his first. This is 57, so this is early. So the wind velocity has to match the wave velocity. Yeah, if it's not matching that direction, you take a component. So this theta is very important. Now I don't know whether you have observed the wind wave generation phenomenon in the field. If you look at the ocean, what you find is that when the wind first blows, the waves actually are very, very short crested. And when the when the wave propagates a long distance, then it becomes like the wave that you see in the movie like Hawaii 5.0. It's very long crested swell. Swell is very long crested. The crest is very long. Okay, it becomes almost unidirection. Yeah. So the short waves are all generated by wave propagate this direction, wave propagate that direction, and the intersection of the two parts give you the three-dimensional shape. The theory was published in 1957. Is there any evidence to prove it? Turns out, no. Not until we will, yeah. We'll come back to this. Not until I get hold of this set of data. This set of data actually was published in the 80s and the 70s. And these are the tracks. What we have is, this is Long Island, this is New Jersey, and this is Chesapeake Bay. This is Eastern Shore, this is Chesapeake Bay. This is the east coast of the United States. This track are the aircraft flights. NASA had made a radar. This radar beam is like a pencil. Now you carry, the aircraft carry this radar scan back and forth as the airplane flies. So you scan the ocean surface right under you. Once you fly that long a distance, you keep on mapping the surface like this, and then you get a surface contour. Then from that surface contour, you do two-dimensional FFT to get the direction of wave spectrum. They fly this way, fly that way, fly this way. And it was amazed to find that when wind blows in this direction, the wave is not propagating in this direction. Yeah, waves propagating in a different direction. At that time, when the paper was published, all this paper was published, was explained in a very different way. They said, okay, the wave is the airplane flying this way, then the wave actually come from that direction because this part is further, and the wind blower degenerates a little bit wave. The wave will radiate to all directions. So the wave propagating this way will give you that direction. That was the explanation. By the time of 1990, I read the paper and I thought about it. I find that the explanation is not very good. Okay, I want to get the data, original data, and actually analyze the original data. I saved the data with maybe a couple weeks to spare. This is one problem with the digital system. This data was collected with a Hewlett-Packard computer. It was in the 70s. And the computer, after 10 years, didn't want to use the computer. They changed the computer to a different one. And the data is written only with the format that computer can read. And the computer has already been pulled out of the rack and put in the storage. When I find this, I want to get the data. I said, well, read this tape for me. He said, nobody can read it. So where's the computer? Computer in storage. So I went to the storage room to pull the computer back and put it on the rack and read the data. Okay, let me show you what I got. When I got this data, I was so amazed to see that the wind actually is blowing this direction, which is offshore. Okay, and you see the energy is here and energy is here. It's not in the direction. The direction of wave has no energy. Yeah, and and the previous person analyzed this. He did not he did not explain this way. He used a scissor to cut this off and put this over here. Because the directional spectrum has a 180-degree ambiguity. You can either put it over here or here. So he put it over here. The reason he put it over here is that, well, that's from the ocean side, the swell and whatever. Yeah. So nobody pay attention to this. When I get the data, I find the symmetric pattern, and I find that if we look at this way, this is the locus of omega equals k dot u. Yeah. This when the projection is over this side. If you take a dot in this side times the cosine theta, this is the component, and that match up this phase velocity, the group phase velocity. So when I get this, I was so amazed. This is at a distance 37 kilometers. In the past, you will never be able to get wave data so detailed. Because 37 kilometers in the ocean, there's no place for you to put any instrument to measure the wave in such a detail. Yeah, this is probably the first good wave data that anybody ever got, and that gives you that the peak energy is on the two sides of the water wave. And this is 37, and you go further to 55. It comes through, actually, see, this original energy was here. Our original energy was here. Now it moved to here. It moved in this way, not in the any other direction. It's moved along the horizontal line. In other words, it's totally agree with k dot u. K dot u equal to omega. Yeah, that's so amazed, and it's still not in the direction of wind. If this is 55 kilometer, you keep on doing until you go to 100 kilometer, then it moves into the direction. Yeah, this is when I got this result, I was so amazed, and I showed it to Professor Phillips. He cannot believe his eye. He thought, because lots of people say, well, we will never get enough data to confirm his theory. And this is the first set of data that actually confirmed. You keep on going, it's still there. But now you see that the frequency is here, and if you go, it's move closer. That means move closer means frequency decrease, and that means it propagates faster. Yeah, wave is growing longer. So the whole, then you compute the angle. This is a theoretical angle based on Phillips' theory. This is an observed angle. It's all along this with some scatter, And the whole issue is that is the wave spectrum moving this way, or the wave actually is generated here, move that way? Yeah. If wave is generated here, short wave in the direction of wind, and keep propagating, getting longer and longer to move this way. But the actual observation means the wave actually move from this direction and that direction to the center, and then move inside. This is the observation. This is the assumption. Okay. All the wave people claim that they can predict wave are all based on this model. Why it works? Because the model has so many different adjustable parameters. You can adjust it to make it actually almost work. And you think the wave model people claim that their model is so good. The model has physics, and physics including the high order wave-wave interaction. Yeah, all the high order wave-wave interaction involve wave numbers, a 4 wave number dot product to satisfy certain condition. And if the wave are actually here, the angle distribution is totally different from the angle distribution from there. It's totally different. Not only is totally different, this direction influence another thing. The other thing is the stress. When the wind blow over the surface, what is the stress? How much stress, how much drag it causes by the wind? Okay, so in the past, stress equal to this is the way to write. Stress equal to rho times u prime I from uj prime. This is Reynolds stress. So the stress depends upon the turbulence velocity component of the air. And this is ui times uj. So it has two directions. Indeed, stress is a tensor. A tensor always has, you need the two directions to define. So two indexes, I and j. But the stress people study stress in the ocean. They write stress as tau equal to CD times U10 and times U10. So I measure the velocity at the 10 meter. I multiply the velocity by itself. Okay, and then I pick the velocity direction to give me the direction of the stress. This stress is a vector. It's not a tensor anymore. Yeah. It's always parallel to the wind. Why? Why it has to be always in the direction of wind? Yeah. If the roughness is caused by wave, if the wave is not in the direction of wind, the stress has no reason to be in the direction of wind. Yeah. So all this assumption, I think, are problematic. So most people say they study wave. Now we see they are not studying wave physics. They are studying mathematics. Yeah. They have a mathematical model, and they study the mathematical model rather than study the actual physics. Actual physics is very different from the assumption they made. Yeah. But the physics is what we should understand. We really need something dramatically new for wave study. But that tool is not available yet. Yeah. We can use this new tool to study wave, but we use new tool only to study the wave in observational data. I cannot study the wave in its analysis. Yeah, that's the difficulty. And so we have a big problem. Now, why we study wave? If you go to any oceanographic institute, you will most likely see their logo, their names, the design of their name that has certain pattern. If it's ocean related, you invariably will see a few wavy lines to show that it's wave, indicate they're steady ocean. But then when you talk to them, you find that very few people actually study wave. They think wave is irrelevant. Wave is not important. Yeah. Why the wave scale is so small? Look at the current. The current system is across the ocean. Yeah. And the wave is not important. So in most of the oceanographic institute, if it has a big institute, like we have 100 people, you may find 1 or 2 people worry about the waves. Most people are not worried about the waves. But it turns out the waves are of critical importance in the dynamics of upper ocean. Surface layer. Yeah. In the surface layer, the wave energy is so strong. And that is bigger than any of the any other type of motion. So those upper ocean turns out are the part that actually make the ocean move. What is the current? Current is first wind blowing, move the surface layer. The surface layer transfer momentum to deeper and deeper layer. So then the whole ocean has energy. So the surface layer is the key to understand the dynamics. Yeah. In the past, people say, I don't care, I parameterize it. How they parameterize it? They say tau equal to a coefficient times velocity square. And that's how they do it. But if you look at this water wave, the surface wave are the most energetic motion. No motion is more energetic than the ocean wave, because the ocean wave, as we see, the ocean wave, when they propagate, the phase velocity equal to wind velocity. That's huge, that's very, very high velocity, 10 meters per second. Nothing approaches that kind of velocity. And wave surface drift current is important, because the drift current eventually transfer the momentum down to deep. And the most important thing is the breaking wave. Yeah. The wave build up. When the wave breaks, it dumps all the energy into the water and becomes turbulence, contribute to mixing, and when wave breaks, the whole tip turn over. The tip propagate the phase velocity. That's 10 times the any other velocity. And once they get there, by conservation of momentum, it has to go forward, right? So all of this make wave so important. Yeah. See, wave energy and momentum, BOE estimate. BOE is back of envelope. That means very simple order of magnitude estimate. Then we'll see that if you have water wave, if you have water surface, you don't consider wave. What is the surface velocity? Surface velocity is a friction of the wind velocity. It's called the frictional velocity. It's a few percent of the wind velocity. So the energy is proportional velocity square. And velocity equal to CD times U square. A CD is 10 to the minus 3. Typical CD, drag coefficient is minus 3. Why it's minus 3? Because the density of the air and density of water is 1 to 1,000. Water is 1,000 times more dense than air. Yeah. So your velocity is very, very small. This is the density ratio. Yeah. And that's the fundamental physics. You cannot overcome that. Yeah. So the drift current is really, really very small. However, if you have wave, look at the wave particle velocity. Wave particle velocity is 2 pi times A. A is the amplitude. So water wave goes through circles. Okay? So the amplitude is A, then the whole circle is 2 pi times A. And how long did it go to one circle? In the time of t. Then 2 pi over t is sigma. So the water velocity, particle velocity is A sigma. Yeah, it's very simple to get. Therefore, what wave energy is A squared times, is roughly equal to A squared times sigma squared. Yeah. Then we divide it by K and multiply by K. It's A squared K squared times sigma K. So it's A squared K C squared. This is phase velocity. We can multiply U star divided by U star. So it's the slope times phase velocity over U star square and times U. This is the surface current velocity. So the ratio of wave velocity to current velocity equal to epsilon squared times phase velocity over C0 over U star. What is this value? This value is almost 1,000. Yeah. So wave energy is 1,000 times the slope square. What's the slope square? Slope can be of the order of 10. 1/10. Okay, so this number is not negligible. Yeah, so that means the maximum wave, AK, is pi over 7. Yeah, pi over 7 is almost half. Yeah, so the wave energy, as far as energy is concerned, on the surface, nothing is more powerful than wave. Yeah. If you, I remember when I was teaching, I tried to study the sediment movement in the coast. And a student of mine, I assigned him a PhD dissertation to actually measure the direction of sediment movement. We built a sediment trap with steel angle, not very strong steel angle. It's about an inch on each side, inch by inch steel angle, a tripod. And on top of that, we put a small sediment trap, like the I think it's about that, with different openings. We have 3 of these traps: surface layer, middle, and bottom. And we went out and put in the coast region to try to measure the sediment in the wave tidal region. The wave was so strong, so the wave hit on the tripod, it actually bent the whole tripod. I tried to bend the tripod back, I cannot do it. Yeah, so that's how strong the wave is. The wave energy is just tremendous. Yeah. So you look at this, you see the wave energy is really strong because the c is the wind velocity. Yeah. This u star is wind velocity multiplied by that. So it's 1,000. Now, this is energy. But momentum, however, is a different story. Why momentum is a different story? The wave momentum, the wave is going in circle, so the average direction is very small. Yeah, but the water current keep on going direct. So this energy and momentum is very different. See, momentum of current is proportional to the current velocity. Momentum of the wave, in water wave, energy equal to momentum times phase velocity. Because energy equal to this, so momentum equal to wave energy divided by c. So it becomes a squared k squared c. Then that's because c over u times u. So this becomes first power. So wave momentum versus c equals epsilon squared times c over u star. This is of the order of 30. U star is of order of 100 or more. Okay, so this value becomes 1/10. So the wave has a lot of energy, but no momentum. So if you're worried about the ocean current, wave is not important. But if you worry about the energy, wave is important. But then ocean current is momentum. So therefore, should I say that I neglect the wave? No. Because the surface mixing that make the current go deeper. The surface mixing is energy. Because in the ocean, the surface layer, the temperature is very different from the deep ocean. On the top surface is very warm, and you go deeper, the ocean is 4 degrees C. Why 4 degrees C? 4 degrees C, because 4 degrees C, the water is the densest. Yeah. So the heavy water sinks to the bottom, and light water stay on the surface. And this is called the thermocline. Yeah. Most of the motion is on the surface. It's not in the bottom. The bottom is almost stationary, very smooth, very slow. And if you want to try this, you can go to any pond, any citang. If in the springtime, you go feel the surface is pretty warm. You move your hand down, the water is much, much colder. So any water, big body of water, the surface is not, the water body is not uniform. Yeah. So this gives you a very simple estimate of what kind of energy is in the water, what kind of momentum is in the water. Yeah. And if you talk about current, you have to talk about the mixing, because the energy is put in the surface. How can energy get it down deeper? It's due to mixing. And mixing is energy, because the surface water is warmer. Warmer water has a lighter, lower density, and cold water is denser, has more, is heavier. So by mix, you take the heavy water on top, mix with the lighter water. That's take energy. That doesn't take momentum, because the water is still there. Yeah, it's not moving anywhere, it's still there. So the mixture is actually energy concern. So we have momentum equal to this, energy equal to this. So we will see that the energy is primarily in wave, but when your wave are breaking, it's very different. The wave breaking depends on how much of the wave is breaking. Not everywhere it's breaking. When it's breaking, only the crest of the wave crashed, and that's the portion of the energy that's involved. So the breaking wave, it's proportional of the breaking part, and that the breaking part depends on the how high the wave becomes and how often the wave breaks. So that is something which we do not know, and people now has empirical formula, but the empirical formula is not very good. And right now, the ocean circulation people start to think through this after 20 years of my arguing with them. Next February there will be a conference here with the Princeton people coming from the United States to discuss this. So if we start to see breaking, we have to know the portion of the surface wave that's breaking. Yeah, and once it starts breaking, the portion of breaking increase tremendously. It can actually approach to half of the surface is under breaking. Yeah, this is the steepness. If the steepness is low, it's only 100ths or thousandths. So it all depends upon how steep your wave is and what kind of breaking. And you can see the significance of this. I will show you. This is one of the first ocean circulation people that start to pay attention to wave. Yeah, and this was done at the Qingdao in mainland China. I like this result very much, and this result is actually published in the Oceanographic Journal in the United States. This Levitas is a scientist at the in the United States Scripps Institute. He spent all his life collect historic data, and the data he collected is just humongous. Okay, and then from that data, because it's historic, it's the total average of what the ocean should look like in long term. And so once you get that, then all the model has to compare with this historic data to see whether it's correct or not. Okay, so Princeton people use their model, the Princeton model, to simulate the global circulation. After you made the circulation, you can compare you can compute the surface temperature. Okay, and you compare that, you get that modeled temperature, you try to compare with the observation. This is the difference. The comparison of modeled surface with the historic data. What you see is that the whole polar region they were very much wrong. Yeah, by a few degrees, the temperature. Yeah. This is very, very critical because you talk about the global warming. Arctic and Antarctic hold the key. Yeah. Our global temperature, that's another problem. If we have time, we can talk about. The temperature of the Earth is the lowest in the last 60 million years. Yeah. Why? Because the Antarctic is isolated. Prior to that, 30 million years ago, this is connected. This is connected. Yeah. And when these two are connected, what happened is that the ocean current cannot go through this. Ocean current have to go up and return. Yeah. Ocean wave go up and return. So the cold current and warm current will actually circulate around. So 30 million years ago, there's no ice in the polar region. Not in North Pole, not in the South Pole. The whole world is ice-free. Yeah. But then, because of the plate tectonic, the Tasmania opened up. The Australian plate keep on moving north, and the South American keep on moving north, and we generate a gap. Once we generate a gap, the ocean current can go flow all the way through. So the cold water will never go to the warm part, so the warm water will not coming back, and the South Pole get isolated. The first place that the ice appeared is the South Pole. Yeah. So, so this is a tremendously important. So if you model this with whatever consideration, you see it's over there. Why it's wrong? Because the mixing. There's not enough mixing. The surface water stays the surface, it never sink. So the temperature is all wrong. And when temperature is wrong, then you cannot using that model to predict the global climate change. If you consider wave motion, then this is the model. The wave contribute to motion, to mixing, and look at the difference. Yeah, but still, there is still overall it's a little bit on the high side, and the mixing is still not enough. If you consider breaking, it will generate even stronger mixing, and sometimes the mixing is too strong, and this is because the breaking wave part is probably overestimated. Yeah, but either way, once you consider the wave motion, this difference is dramatic. So that is why I think we have to study wave, and the wave actually make a difference in the physics. Yeah, and when we study wave, we'll find that the way that we study wave is not actually physics, especially after using HHT. Yeah, and so now you have gone through this HHT course. You will have a better tool to appreciate the difference. Yeah. So when people talk about this, you can have an intelligent ground base to form your own opinion. Yeah. So that is the first. I study HHT, start from wave problem. Yeah. Now I give you my path from the beginning to end, and I give you summarize my understanding of the wave and its impact in the global geophysical problem context. Okay, so I will stop here today. Next time, I know most of you are. How many of you are from civil engineering? None? Oh, only a couple. Only 3. Yeah. Next time we'll talk about. I'll give you a problem on bridge, and after bridge I'll talk about the problem on airplane. Yeah. And if we have time, we'll talk about the problem in a human body. Okay? All right. Thank you very much. Yeah.